Okay, so many weeks ago we were doing graph properties. So independent set is where we stopped. So this question of finding maximum independent set and the dual problem of finding clique, maximum clique in a graph, and a third problem of finding a vertex cover in a graph, right? So these three related problems we had studied. Okay, so now we'll move to a related problem and then show some quantitative relations between stability number and that. So that problem is called coloring. So this we have mentioned many times. This is the question of coloring the vertices of a graph so that no two adjacent have the same color. So edges should not become monochromatic, basically. Right, and we have seen, again we have mentioned many examples. Just to repeat, this example of scheduling exams so that in different halls, examination halls, so that no two students sit in the same hall if they are friends. Right, so here again the halls, I mean you can take courses as vertices and you can draw an edge between two courses if there is a common student. No, sorry, not that. Here you have to draw an edge. Yeah, vertices will actually be students, and if they are friends you will draw an edge. So student 1 and student 2 you draw an edge if S1, S2 are friends. So vertices are students, and where are the halls, examination halls in this? Yeah, so here the colors will be, so examination hall 1, 2 and 3 you can then say that we'll color vertices with 1, 2 or 3, and you don't want an edge to be monochromatic, which means that a friend pair should not be in the same hall. So examination hall numbers as colors. Right, so these kind of examples are there. We have already mentioned these examples. So now we want to study this as a fundamental graph property, which is given a graph. What is the minimum number of colors that it needs? So formally, given graph G, a coloring is a map from a set of colors to V, from V to set of colors. Such that so let's say the map is C, such that if UV is an edge, then colors should be different. Okay, so this is the definition of a valid coloring of a graph, or simply coloring of a graph. So it assigns colors to each vertex such that two vertices adjacent means that they get different colors. And minimum number of colors needed for this Now this, note that this minimum number is unique and it's well defined, because what is the trivial coloring of the graph? Yeah, you just send V to V, right? N vertices, so you color every vertex with a different color. So that clearly is a valid coloring. So coloring, the minimum number will always be less than equal to N. Is there an example where it is N? Complete graph, right? In a complete graph it is N, so it can be anything between N and 1. So it will be unique, this number will be unique. And this is called chromatic number. So chi G. Right, this is a number between 1 and N. Okay, so for example, if you look at the graph of, or if you look at a map of countries or states, then the corresponding graph, this I had stated, this is a major theorem in graph theory, that a graph that comes from a political map, that can always be colored with 4 colors. Okay, this is a giant theorem which was proven by Apple and Harkin. In 1976, they used computers to actually check some remaining cases. So it was not a completely mathematical proof. In fact, it is called the first proof that used computers to complete the proof. Part of the proof was actually looking at cases through computation. And then later on, some other proofs were found. So there are multiple proofs now which don't need computation or exhaustive search. Yeah, but this is only for information. We will not discuss this or ask questions about this, because this is a very complicated proof out of the scope of this course. And similarly, this example that we took, where you look at the social graph and color that, so that will give you the chromatic number of that graph will give you the number of examination halls. So in the social graph, the chromatic number will give you the minimum number of halls. Right, so in this case it will not be fixed number, it will really depend on the class and how the friends are distributed, right? So based on that the chromatic number will change. It's not like the map of countries or states, where surprisingly you get something as universal as 4. So in general, this number depends a lot or completely on the input graph. And can you think of an algorithm to find this given a graph compute chi G? How do you compute chromatic number in practice? So this is an extremely difficult question. Okay, there is no known algorithm which will do fast. Because the chromatic number can be anything between 1 to n. So suppose it is k, to actually check for that you have to try all possible colorings using k colors of your graph, right? And how many ways are there to use k colors on the vertices? Something like n choose k, n to the k, right? So if k is around, let's say n by 2, is it k to the n? Yeah, either way. So when k is in the middle, say n by 2, then it becomes the hardest. You basically have to look at n by 2 subset of the vertices, and that there are too many. Or to be precise, in the n by 2 colors case, you have to look at various subsets. All possibilities are there, so it becomes kind of n to the n. So computation is very hard. That's an open question. In a fast way. Okay, so there is no fast algorithm, and none is believed to exist as well. These are one of the harder problems in computer science. Okay, so more examples about this. What is the chromatic number of a cycle? Cycle on n vertices. So if n is equal to 3, then what is the number of colors needed? Yeah, in this case it is 3, but if you have a square, then then you can manage with 2. So what is the correct answer then? Yes, so then it depends on parity of n, right? So it is 3 for n odd, but for n even it is just 2, because you can alternate 1, 2. And what about bipartite graphs? So k n comma n, what is the chromatic number for a, sorry, I should not say the complete graph, but actually even this is fine. So you have x and y and you have n vertices, and all the edges are there, right? Even with all the edges, it is just number everything here with 1 and here with 2, and that, which is fine. So you get answer 2, which means also for any bipartite it's 2. It cannot be bigger than 2. It's either 1 or 2. When is it 1? Yeah, it can only be 1 if there is no edge in a graph, right? Okay. Right, so one simple property that you can deduce from the definition is that vertices that are colored with the same color, say 1. So let me call this chi inverse 1, right? So look at a color, say 1, and look at its pre-image, which is all the vertices which are colored 1. What can you say about the edges on them? There is no edge, right? So chi inverse on any color is independent set. So basically coloring contains many, gives you many independent sets. For every color you see these independent sets. And hence coloring is equivalent to partitioning. Let me say more precisely. So chi of G equal to K means that G can be partitioned into K disjoint independent sets. Right? So for every color 1 to K, you get these independent sets, they are disjoint and they partition all the vertices. Right? So the graph, the vertex set and hence the graph gets partitioned like this. How about the converse of this statement? If you partition the graph into K independent sets, can you say that you can color with K colors? Yeah, so we can make it less than equal to. And based on that, you can get the converse. Right? So coloring is equivalent to actually partitioning into disjoint independent sets. Okay. So based on this, we should guess a relationship between chromatic number and stability number. Right? So let's prove that. So we'll prove that the stability number of a graph times the chromatic number is at least the number of vertices. Is it clear? So the product of stability times chromatic is at least n. And we'll see examples of why this inequality is required. We would want equal to, but that is not true. How do you prove this? It has a very simple proof. So you just use the previous property. So let the optimal coloring of G partition V into V1 disjoint union V2 disjoint union Vk, where K is the chromatic number. Okay, and these VIs are vertex subsets on which you get independent sets, and they are obviously they are disjoint. That's the partition, and they are K many depending on the K colors. So on the left hand side vertices there are n, right? And what do you get from the partition? What is the size of Vi? Yeah, by the definition of stability number alpha G, each Vi is at most alpha G, right? So you get K times alpha G to be at least n. So this means that size of V, which is sigma Vi, n is V is n, and VIs are in less than equal to alpha G, which is K times alpha G, which simply means that n is less than equal to chromatic number times alpha G. Is that clear? You immediately get this. Now, why is this not an equality? Can you think of a graph where the chromatic times stability is greater than n? How about this? Right, so this triangle with an edge removed. What is the stability number? And what is chromatic number? Sorry, somebody said 3. Yeah, 3 is a waste. You can manage in 2. 1, 2, and 2. So this is 2, and number of vertices is obviously 3. So you get that the product is 4, which is more than 3. And yeah, so this equality will not work. Can you show an example where there is equality? Complete graph. The independent set is 1 and chromatic, yeah, that's good. Okay. So complete graph has stability 1, chromatic is n, so the product is n, right? So the theorem we proved is an optimal theorem. It can achieve n and it can also be more than n, so cannot improve that. More interesting example here you can take as the hexagon. So here the chromatic number is what? This is C6, right? So you can color in 2 colors, just alternate. And the stability is 3, right? So 2 times 3 is 6. So that's also, it's a smaller example. Okay, a more interesting result will be relating chromatic number to the degree of the graph. So let's say G has maximum degree K, then the chromatic number cannot exceed K plus 1. Okay, maximum degree means that you go over all the vertices, and what is the maximum degree? Maximize over the vertices. So for example, if your graph, the degree everywhere is 3, then you don't need more than 4 colors. Okay, 4 or less will suffice. So that seems to be a useful property, because for low degree, you now can see that the chromatic number is small. And the graphs can still be very complicated, because saying that the degree is 3 doesn't mean that the graph is simple. A graph can have million vertices and very complicated with degree just 3. And moreover, if G is connected and there exists a vertex in G with degree less than K, okay, so maximum is K, but there are also vertices, at least one vertex where it is K minus 1 or less. Maximum is not achieved and the graph is connected. In that case, chromatic number is smaller. we'll show that it's at most k. Okay, so we'll prove these results. So any ideas for the first property, the main relationship between degree and chromatic number? How do you show this? Have you learnt any method that you can use? Yeah, so evergreen method is induction. We'll induct on the size of the graph. Okay, so for the first property, let's apply induction. On the number of vertices, which we'll call n, number of vertices on this graph. Graph was G, yeah. So call that n and we'll induct on this. What is the base case for induction? Well, the base case is if you have only k plus 1 vertices, then clearly the result is true, right? If you have k plus 1 vertices, then the degree that a vertex can have is at most, there can only be k neighbors, and you can just color every vertex differently. So this is trivially true. N less than equal to k plus 1 is covered. So we only have to consider bigger than this, bigger than k plus 1. So in that case, consider a vertex. Actually, you can take any vertex. Let V be any vertex, and look at the neighbors of V. Okay, so look at this graph that comes out of G by looking at the neighbors of V. I don't want to see the neighbors. Yeah, I should just delete V. I should not look at this. Let me not draw this picture. Consider G prime by deleting V from the original graph. So now basically the vertex V is gone, vertices are now n minus 1, and all the edges incident of V are also gone. Right, so this is basically it's V minus V, and its edges minus the neighbors of V. That's the graph. Okay, so both the vertices and the edges are, vertex set is definitely reduced, and possibly edges are also reduced if we had neighbors. Right, so this is a smaller graph, you use induction on this. What will induction give? Yeah, so you have to first check what is the maximum degree in this in G prime. The maximum cannot increase, right, because you have deleted a vertex and edges. So maximum remains k or less. So chi G prime is less than equal to k plus 1. So by induction hypothesis, you get that chi of G prime is less than equal to k plus 1. But you wanted to study chi of G. How do you show that? Yeah, so let us, so G prime, basically all the vertices are colored except small v. So let us look at what we can do with small v. So small v has edges E1, E2, how many edges? At most k, right? And these vertices, the vertices which are being touched, they are part of G prime. So those are already colored. Right, so which means that the neighbors have already used up k colors. So how do you color V? Yeah, so one color is free. So you use that. So neighbors n of V use up at most k colors, which means that V has a color free, has greater than or equal to one color free or available. Hence you deduce that chi of G is also less than or equal to k plus 1. Is this clear? Okay, so simple induction and you get the result. Sure, yeah. They can all be same color. That we had an example, right? We had this example of partial triangle or star. In a star, all the neighbors have the same color. That is possible. Okay, so now how do we improve this by one color? We have to use that G is connected and there is a vertex with k minus 1 degree. Sorry? No, strictly smaller than k. No, otherwise it will be the same case as above. I mean, connected is also there, but the degree being k minus 1 or less is important. So we'll do the same proof. I mean, we'll do a similar induction. So for part 2, we'll use induction on n and improve. Using this degree of V to be less than k. So now we are given essentially the V which we should pick and then induct. The V is whose degree is small. So what happens when you induct with respect to that? So again, G prime is G minus this vertex V, and So now when you G was connected, but what about G prime? This may not be connected, right? If you remove a vertex which was a bridge, then the graph becomes disconnected. So let there be connected components. So let H1, H2, HL be its connected components. So now the picture is you have V and you have connected components here. And the connection from H1 to H2 is via bridge given by V. This is the whole graph G. So how many edges are incident on V? K minus 1 or less, right? So let's say K minus 1. So V has these many neighbors. Now the neighbors may, of course, they may be in the same H1 or they may be in different HIs. That won't be important. So what do you do now? How do you use induction? So what can you say about H1? Yeah, first of all, H1 is connected by definition. And what is the max degree of H1? That's again K. But is there a vertex with degree less than K? Which one? Exactly, the neighbor of V, right? So, and there exists, say, a vertex V1 in H1 with degree less than K. Is this clear? Any questions? So the neighbor of V, call it V1. There is a V1 here, or maybe it's better pictorially. So the connection of V in H1 is to V1, and when you look at just H1, then the degree of V1 is well, maximum it can be K, but it cannot be K because one edge has been deleted. So it can be maximum K minus 1 within H1. Within G, it is possibly K, but within H1, it is possibly K minus 1, not more. Right? So that is the one. So what does induction give you? So the induction hypothesis on H1 gives you the chromatic number. So chi of H1 is less than equal to K. Right? And then you repeat this. So you will get that chromatic number of Hi is less than equal to K for all I. Is this clear? What do you do next? How do you deduce chromatic number of G? H1 to HL, they have been colored within. So all that remains to be colored is V. How do you color V? Yeah, the neighbors of V are only k minus 1, they have been colored. So one color is free. Same as before. So neighbors NV, they use up k minus 1 colors, which means that V has at least one color free. So you use that color, color the graph G, getting chromatic number at most k. Any questions? Right, so that is great. Now you have a good relationship between degree and chromatic number. So degree k basically means chromatic number k or less. This gap between k plus 1 and k, can it be improved? Can you say that maximum degree is k, but chromatic number is only k? Always. Is it possible? Right, so if you look at a complete graph on n vertices, then the degree is n minus 1 and the chromatic number is n. Right, so hence the first property is optimal. You cannot improve it. In general, it cannot be improved. What about the opposite case? Are there examples of graphs where the vertices are a lot, it's connected, but the chromatic number is very small? So basically high degree, but chromatic number very small. Are there such examples? Sorry? One which is, you mean star? Yeah, so star has high degree, unlimited number of vertices, but the chromatic number is always 2. Right, so these connections are not extremely tight. It depends a lot on how the graph connectivity is. You cannot just look at the count and deduce chromatic number. Neither the degree nor n will be conclusive. So again, in the case of star, on n vertices, the chromatic number is just 2, whereas the degree is n minus 1 and vertices are of course n. So you can take n to be 1 million, still the chromatic number is only 2. Right, so there are properties of chi that we have seen, but these properties are not powerful enough to actually give an algorithm, because you still have to look at the very specific graph that you are given. And there are many graphs on n vertices, so that makes it harder to characterize. Any questions? Okay, then we will move to a different construction in graphs or structure in graphs, which is called matching. And this is particularly important in many areas of computer science, starting with algorithms. So there are tons of matching algorithms. that people implement and solve real problems. So what is this object? So we start with an obvious example, which is suppose you have two teams A and B. So you want to have a tennis tournament between teams A and B. So A has some n members and B has some n members, and so a member from A will be played against some member in B. Members in this tournament are ranked by their level or by their expertise. So basically, a member in A will have a list of members in B, players in B, who are of the same or comparable level. So this person can play only with those people. Okay, so this bipartite graph is given to you. So given the graph of player expertise, or maybe player pairings, let's say. G, which is A, comma B, comma edges. Right, so it's a graph where you have players 1 to n in X in A and in B. And one can play with some people here, and two can play with some other people, and n can play with those. So every player in A has a analog subset of players in the other team. So what you want to find out, I mean, you want to schedule these matches, right? So you want to find out how many games can you schedule that can be played simultaneously. Okay, that's the question. So what is the maximum number of matches that can be held? And imagine, I mean, you can assume that the number of courts is infinite. So court will not be the restriction. Time is the restriction. So you want to minimize the number of days, right? So in a day you want as many matches as possible. So maximum number of matches that can be played simultaneously. Okay, so being able to play simultaneously is the important keyword. So how do you solve this problem? You are given an explicit graph. How do you find the number of maximum simultaneous matches? They correspond to what edges? Green edges. Well, clearly, player 1 can only play simultaneously with one person, right? So you are looking for edges that are disjoint in terms of endpoints, right? You want non-overlapping edges, maximum possible. That will be the schedule for day 1. So that is find maximum number of non-overlapping edges in E. Right, so this subset that you are looking for, this is called a matching. It's a matching from players A to player B. It may not cover all the players, but we want maximum, so it is called a maximum matching. Number of players can also be different, so there is no reason for them to be same. So whatever is the setting, is the input, you want to find the largest possible matching. So let us now define it independent of the game. So matching M in a bipartite graph X, disjoint Y and the edges across is a subset of edges such that no two edges share a vertex. Okay, so that is what is a matching. So in this case, an edge, basically, if you pick an edge, then it means that you are creating a match, a tennis match between these endpoints. So let's say U and V, player U from A, respectively player V from B. And then you want, if you pick two edges, then you don't want them to share any player, right? So they have to be disjoint endpoints. So that is what is meant by two edges not sharing a vertex. And maximum will be when you make the size of M maximum. So maximum matching M is the largest possible in size, in number of edges. And what is a maximal matching? Yeah, so as we have seen before, sometimes the difference between maximum and maximal is that maximal cannot be grown. So which means here is that matching such that for all edges in E minus M, so for all the remaining edges, if you try to add this edge in the matching, what happens? Then it is no more a matching. Okay, so maximal is basically, I mean, definition is very algorithmic. So somehow you have found a matching in which there is no scope for growth. You try to add any edge, it becomes non-matching, right? So it is maximal, but then it may not be maximum. Do you have an example? Why are these two concepts different? Sorry? What's a Z? How many vertices are there in X and Y? Just 2. Okay, how do you do in 2? And then you add these edges. So I wouldn't say X, I wouldn't say Z, it's more of an X. So here if you take this edge to be in the matching, if M is 1, 1, right, then what happens is, and there are 3 edges in the bipartite graph. So there are 2 more edges which are dotted. If you add dotted edge, then the problem is that it will overlap with M. So you cannot add, right? So this M is maximal. Yeah, that's not a good example. It's also maximum. No, sorry. Maximum will be that you take the complement. You take 1, 2 and 2, 1, right? So this works. So in this graph, where the edges are 1, 1, 1, 2 and 2, 1, if you take M to be 1, 1, this is maximal, but if you took the other ones, 1, 2, 2, 1, this is maximum. Okay, and it's larger. So M is maximal, but it is not maximum. For maximum, you have to take something totally different. So if you are doing, if you're thinking of this algorithmically, then if you pick the wrong edge to begin with, then you are stuck, because this wrong edge will only take you to wrong places. Right? You have to actually throw away this edge and start afresh with totally different edges to get maximum. So which is why this optimization problem is not so easy. Do you know of any algorithm to solve this? How do you find maximum matching? In fact, first of all, how do you find a maximal matching? How do you find maximal? Well, you just pick any edge and you keep adding edges till you cannot add anything. Right? So it's a simple for loop. So this is a very fast algorithm to find maximal matching. It's direct from the definition. Now, what's the algo for maximum matching? How do you find that? So this, of course, is problematic, much harder than the previous question because of these examples. Right? That if you started, if you don't know which edge to pick, then your choice can be so bad that it will never expand to a maximum. Right? It's basically a bad starting point which will keep you in a local maxima, which will be much smaller than the global maxima. But believe it or not, there are very fast algorithms for this. Okay, so it is non-trivial, but there are famous algorithms for this. So it can be solved in a completely practical way. So why is that? This we will see next time. Okay, we'll prove some properties of matchings which allow this algorithm, although we'll not see the algorithm because that is a subject of different courses.